Hi, welcome back to this PI-KEM video series covering how to create the perfect coin cell. I'm Georgia, and in this video we'll be covering the final stage of coin cell manufacturing, cell assembly and crimping. In the previous videos, we've prepared our electrode slurry, coated and calendared our electrode sheets, and cut them into precise electrode discs. Now, our perfectly prepared electrode discs will be assembled with other components and crimped to complete a final electrochemical cell. Crimping not only seals the cell, but also ensures the internal components remain properly aligned and compressed. A well-assembled cell provides good electrical contact, a reliable seal, and the consistency needed for meaningful battery testing. In this video, we'll walk you through the structure of a coin cell, the correct assembly sequence, and how to achieve a reliable crimp that produces a sealed, test-ready cell. Before assembly, it's important to understand the role of each component inside the cell. The CR2032 is one of the most widely used formats in coin cell research. The stainless steel case provides structure for the cell and serves as the external electrical contact. Inside the cell, the separator prevents the electrodes from touching and short-circuiting, while also allowing ions to move between them. The spacer helps to maintain the correct stack height and ensures good contact between components. The wave spring applies consistent pressure throughout the cell stack, while the cap completes the assembly and forms the final seal during crimping. While each component may seem simple individually, together they create the mechanical structure that allows the cell to function reliably. In a real battery manufacturing environment, cell assembly would take place inside a glove box. Materials such as lithium metal and battery electrolytes are highly sensitive to moisture and oxygen, so assembly is typically performed in an argon-filled glove box with extremely low oxygen and water levels. For this demonstration, we're focusing on the mechanical assembly process only. No electrolyte is being added, and the assembly is being shown outside of a controlled environment. Correct assembly order and electrode orientation are critical for cell performance. Begin by placing the cathode into the positive case with the coated surface facing upwards. Next, position the separator so that it is centered and completely covers the electrode. Place the anode on top with the coated surface facing downwards. This ensures that the active material on both electrodes sits directly against the separator, allowing ions to move between them during cell operation. If the electrodes are positioned incorrectly, the active materials can face away from each other and towards the current collectors, resulting in little usable capacity of the cell. Next, add the spacer and then the wave spring. In a functional cell, electrolyte would now be added before the final closure. However, for this demonstration, we're focusing solely on the stacking process. Finally, place the negative cap onto the assembly and gently compress the stack by hand. Position the assembled cell carefully within the crimping die, with the cap facing upwards. The die is designed to apply force evenly around the entire circumference of the cell. Once the cell is positioned correctly, close the pressure valve and begin applying pressure. For a typical CR2032 cell, we use approximately 1000 psi. During crimping, the outer edges of the case is deformed around the gasket and cap, creating the final seal. Too little pressure may result in a poor seal and potential electrolyte leakage. Too much pressure can damage internal components or crack the gasket. Achieving the correct crimping pressure is essential for producing reliable and repeatable cells. Hold the pressure briefly before releasing the pressure valve and removing the finished cell. Remove the finished cell by pressing down on the edge of the crimping die and sliding the cell free. After removing the cell from the die, inspect the crimp carefully. Look around the entire circumference for a smooth, uniform crimp with no visible gaps between the case and cap. There should be no cracks, distortions, or signs of excessive compression. A good crimp should appear consistent all the way around the cell, indicating that pressure was applied evenly during assembly. This is the finished coin cell. It represents the culmination of every stage we've covered throughout this series. With the cell assembled and crimped, it's now ready for electrochemical testing and evaluation. At PI-KEM, we supply everything needed to support coin cell assembly and testing workflows. This includes coin cell cases and components, hydraulic, pneumatic and electric crimping systems, precision tweezers, and decrimping tools for cell disassembly and post-mortem analysis. For advanced research applications, we also supply specialist test cell formats, including Kapton cells for X-ray diffraction studies and split test cells for materials evaluation, alongside a range of battery testing and electrochemical analysis equipment. So that's the final stage of coin cell manufacturing. Throughout this series, we followed the complete workflow of coin cell fabrication, from slurry preparation and coating through to electrode processing, assembly and sealing. Each stage contributes to the quality and performance of the finished battery cell. Whether you're building your first battery research setup or scaling an established laboratory, PI-KEM can supply the equipment, materials and expertise needed to support every step of the process. If you'd like to learn more about any of the materials or equipment featured in this series, visit PI-KEM's website or contact our expert team to discuss your application. Thank you for following the series, and we wish you every success with your battery research projects.